As Aki said, I'm a student of Suhas Patankar's, who is a student of Brian Spalding, so I'm really honored to be a part of this symposium. I'm going to talk a little bit today about small-scale thermal transport, which is contrast with this talk that we just heard about transport at planetary scales. Before I launch into that, let me say a little bit about PRISM, which is the center I run at Purdue University. PRISM is a center that's actually funded by the National Nuclear Security Administration, NNSA, which is the one that funds the labs, Los Alamos, Livermore, Sandia, and so on. But for the work of Frank Harlow and the T3 group at Los Alamos, I don't think PRISM would actually exist. It's their success in computation of very complex systems that essentially had centers like PRISM funded. So I feel connected to both Professor Spalding and also to Frank Harlow here. So at PRISM, what we're looking to do is to look, as Aki said, PRISM stands for Prediction of Reliability, Integrity, Survivability of Microsystems. And so what we're trying to do in PRISM is to predict and understand better failure mechanisms in microsystems, particularly a class of radio frequency microelectromechanical systems, RF-MEMS, a picture of which is shown here, notional picture of which is shown here. What this is, so this is basically a micromechanical switch, if you like. So the yellow thing that you see there is a very thin metal membrane, typically nickel. It's about a micron thick. And what you see there, the blue thing there is basically an RF line through which passes an RF signal. The brown material is a dielectric. And the way the switch works is you apply a voltage between the metal and the dielectric, causing the metal to be activated by an electrostatic force. The metal closes and touches the dielectric. And you can do this either once, or you can do it every few microseconds, depending on the kind of application that you have. Now this thing sits in a fluid, so you're really talking about the interaction of fluid, structure, electrostatics. There are a variety of different ways that this device fails. In the lab, this survives a few months at present, and people are interested, obviously, not interested in devices that only survive a few months. In practice, they want things that survive much longer, and so we want to understand how such a device fails. What are the mechanisms by which it fails? There are a number of postulated mechanisms, one of which is dielectric charging, whereby charges get trapped in the dielectric, distorting the electrostatic field, and therefore causing difficulties in either making the membrane stick and unable to lift off, or unable to close the thing altogether. So there are a variety of nasty computational problems all hooked together. So we're talking fluids, we're talking structures, we're talking electrostatics, charge transport, all of which is meshed together. There are atomistic scale phenomena whereby the physics of contact now change the way defects form in the dielectric, and therefore change the rate at which charges may trap, etc. So I guess the message that I'm trying to give here is that computations now have come a long way from CFD alone or computational mechanics alone. We're now looking really for an understanding and for a set of methods that go across fluid mechanics, computational electromagnetics, hooking to small scales, ab initio computations, molecular dynamics computations, and so on. So that, I think, is really the next challenge in our business here today. One of the things that our center is tasked with is to quantify uncertainties in our predictions. Now, MEMS are famously uncertain. So if you were to make microelectromechanical systems in one lab, in one particular batch, on one particular wafer, you may get one set of dimensions, one set of properties, one set of lifetimes. The same thing created a few days later, or in a different lab, or a different set of processes, would give you very, very different lifetimes, and so on. So there are large uncertainties in dimensions, in material properties, granular structures, and so on, change material properties drastically. And so there's a real question about what prediction actually means. And in fact, no sensible prediction can be made in these situations without attaching uncertainties to inputs and understanding how these uncertainties propagate into our predictions and give us error bands on our outputs. So we're really interested in a class of uncertainty, in uncertainty quantification methodologies for doing this. Then, of course, we have a bunch of very good microscale fluid mechanical data, electrostatic actuation data, and so on, that we think is going to be one of a kind that comes out from the center. What I want to do today, though, is to bite off a small part of this computational problem. I want to talk about small-scale heat transfer and unified methodologies for computing heat transfer that address transport by electrons, transport by phonons, transport by gas molecules, all within a single framework. Our focus is on the mesoscale in everything that I'm going to talk about today. There are established methodologies for very small scale thermal transport computations and other kinds of computations, ab initio, molecular dynamics. There are, of course, well-established methodologies for regular macroscale simulations. What I'd like to do today is to talk about the mesoscale. And by mesoscale, I mean scales from about in tens of nanometers going all the way to 1, 2, 3 microns. Right? Now, so we're interested in looking at coupled electrothermal, gas-solid thermal transport. These occur in a variety of applications. For example, this is a picture of a silicon-on-insulator field effect transistor. It's a transistor out of IBM, where what you see here is that this is the transistor itself. These are your leads. That is a thin silicon device layer. The yellow thing that you see here is a gate. And essentially what happens in this transistor is that electron-phonon scattering, the interaction of electrons and phonons, causes Joule heating in the channel region of the transistor. That's got to transport its way out through an offside insulator to a heat sink that's sitting way down here. Right? And so this is a combination of electrons and phonons interacting with each other. This is a picture of Joule heating in a bulk field effect transistor. So we're interested in the interaction of electrons and phonons here. In other applications, we're interested in the interaction of phonons and gas molecules, for example, in nanoporosilicon or in particle beds, where solid particle contact gives you such high resistance that even a low conducting gas in the interstices becomes a pathway for heat transfer. Right? So we want to understand how these kinds of things work. Ultimately, though, even though we concentrate on the small scale, on the mesoscale, we are interested in integrating these nanosystems into larger systems with which human beings interact. And so, therefore, within this framework, multiscale, multiphysics models, and coupling are essential. And so we're interested in computational methods that address these scales. So what I'm going to do is I'm going to talk a little bit about a unified particle framework for submicron thermal transport, how we're subsuming these kinds of models into larger scale models. So this is models of transistors being absorbed into models of circuits on the scale of several tens to hundreds of microns. I'm going to talk a little bit about work in the gas-phonon coupling area, touch on uncertainty quantification if I have time, and a little bit about the software suite called Mimosa that's coming out of our center, which addresses unified simulation of mesoscale thermal transport. All right, so what is this unified particle framework that I'm talking about? It's easy to talk about this with respect to Fourier conduction, for example. And so if you were to think about a domain whose length scale in this case is L, and if you were to think about transport, for example, by phonons, and if you were to think about them as particles rather than as waves, under a particle view, if the mean free path of the particle, the carrier, is much, much smaller than the length scale under consideration, then these particles, essentially, the carriers interact with each other sufficiently that diffuse transport obtains. And so in this limit, you're really talking about continuum behavior. Fourier's law is valid. Comparable to or competitive with the length scale under consideration, then these particles encounter the boundaries of your domain much more frequently than they encounter each other, and so in that limit, Fourier's law would be invalid. Right now, so we're really interested in domains in physics that address this case. Now, if you look at a typical thermal transport, it could be by phonons, it could be by electrons, it could be by gas molecules, but you can describe all of these transport mechanisms through similar kinds of considerations, typically through, for example, here we show you the Phonon-Boltzmann transport equation, where n is the distribution function of phonons. So this is the transport term On the left-hand side, this is a scattering term, and I'll say more about that in a minute. Electrons have a very similar, the electron BTE, or the Boltzmann transport equation, has a very similar structure. Gas molecules, again, in the rarefied regime, also have similar structures. These equations tend to appropriate diffuse transport equations at the macro scale. So the Phonon Boltzmann transport equation tends to Fourier's law on the macro scale. Electrons would tend to drift diffusion type equations in the macro scale. Gas molecules would give you Navier-Stokes in the macro scale. So this is a framework within which you can go from the mesoscale all the way to the continuum scales in one fell swoop. And so we're very attracted to this kind of a unified idea about transport. So what we're essentially doing is to develop a unified Boltzmann framework that talks about all these kinds of carriers within the framework of modern, unstructured, finite volume methods for solving this class of equations. All of this is encapsulated in a modern software system, C++ code with Python wrappers, and very importantly, inherent in our software is this whole idea of operator overloading, templating, to give us automatically sensitivities and adjoints, and also a framework for uncertainty quantification as well. So what it's allowing us to do is to look at all of these problems in a unified, single-handed sort of way, but also then giving us tools that hopefully we'll be able to deploy to everyone to use. All right, so let me focus a little bit on heat transport in solids, and particularly phonons here, just to give us a way of getting started about this. Now, if you think about, now phonons are basically quanta of lattice vibration. So these are really nothing but waves in a solid, sound waves in a solid really, therefore the word phonons. Now, if you're in a regime typically larger than about the typical phonon wavelength, which is 1 to 5 nanometers in silicon, for example. So if you're talking about 5, 10 nanometers and larger, you can essentially forget about the wave properties of phonons and think about them as particles. Right? So if you can make that jump, then phonon transport can be addressed by the Phonon Boltzmann transport equation, where n is the distribution function of phonons. V is something called the group velocity, which I'll tell you about in a minute. And on the right-hand side is a scattering term. Now, phonons can be characterized essentially by their position, vector, and time, but also by something called the wave vector and their polarization. So the wave vector essentially captures the vibrational modes of phonons, vibration modes of the solid, and P also captures the type of vibration. So what I'm really saying is, so the vibrational behavior of the solid can be captured by something called a dispersion diagram or a dispersion curve, where the frequency of the wave motion is tied to its wave vector, which is k. And all of these different curves that you see here are different modes of vibration, longitudinal vibration, transverse vibration, and so on. So these curves here are called polarizations. That's what that P is about. And k is the wave vector. And so if you look at the phase space that this equation occupies, it's very large indeed. So you've got the usual space and time, but now you've got 3 components of the wave vector space, and then you've got polarizations, which in the case of silicon are 6 in number. You see 4 here because this is a high symmetry direction. The other thing I should say is, so the way to think about phonons is to think about different kinds of particles, if you like. All right? So we've got particles, the type of particle is characterized by its wave vector. So that's a flavor or a color of the particle, and also its polarization. So you can think about these as many populations of different kinds of particles, each of which is transported by the Boltzmann transport equation. So you've got as many PDEs as you've got representations of the types of particles you have. Right? Each of these particles has a different group velocity. The group velocity V is the slope of the dispersion diagram. Right? So it depends on the frequency of vibration, it depends on the kind of polarization that you have, and so each particle group then, characterized by its wave vector and polarization, has a different group velocity. Now, all of you who do computational fluid dynamics recognize the left-hand side of this equation. This is really nothing but the linear wave operator. You all know how to do this. There are all kinds of convective differencing schemes that people, obviously everything that's done in computational fluid dynamics would also apply here. Right? What's nasty about phonon transport really sits on the right-hand side, which has to do with the scattering term. So if you didn't have a scattering term at all, essentially what phonons do is move ballistically, like straight lines, like bullets, with a group velocity v, which is known from atomistic considerations. Okay, so you can get that if you know the atomic structure of the material. Now, so these would move in straight lines if they didn't interact, but they do interact. So they interact with electrons, they interact with other phonons, they interact with grain boundaries, and so on. So there's always scattering. In general, the scattering term is extremely complicated to compute. We are doing it, but generally speaking, this is at least as expensive as solving the PDE itself. And so there's a lot, so people sort of take the easy way out and make what's called the relaxation time approximation, where n naught is the Bose-Einstein distribution, and tau is a time over which the distribution function of phonons relaxes to the Bose-Einstein distribution. So you're left then with the problem of determining relaxation times, which is also not a trivial problem. So to summarize, what are we talking about here? To solve the phonon transport problem, you have to deal with many, many, many different groups of phonons, each of which is represented by a wave vector and a polarization, and each then characterized by a group velocity which can be determined from atomistic considerations, and a relaxation time, the computation of which is not trivial, but nevertheless can be done. So typically we're talking in solving a Phonon-Boltzmann transport equation of resolution in space and time as usual, but several thousand partial differential equations. To really capture the kinds of behaviors that we want to capture, you may talk about 5,000 partial differential equations or more. Right? So that's the story here. So that's what we're trying to do. And so it's a little bit about the connection to the atomistic scale. One of the most difficult things to do here, as I said, is to compute the scattering term. And this can come either from perturbation theory, the theory of transitional states, or from molecular dynamics, simulations of the actual atomic structure. And here I show you relaxation times for one particular phonon polarization, one kind of phonon particle, longitudinal acoustic, as a function of frequency. And the thing that I want you to notice is this enormous spread in relaxation times, orders of magnitude. You have Newton numbers that go over 3, 4, 5 orders of magnitude in these problems. And these are all coupled together. Right? So that's one of the deals. So if you look at typical Boltzmann transport equation models, the whole problem is so nasty and so difficult and so big that people have made all kinds of approximations. So people will think about gray Boltzmann models, whereby you don't worry about all of these different phonons that exist. You lump them all into one gray mess, and you talk about transport of this gray model, just like you might in thermal radiation, for example. People have tried to make small changes to that by talking about semi-gray models, where you might divide phonons into things that move and things that don't move. But we're now beginning to look at fully resolved Boltzmann models, where we actually look at all the complexity of phonon transport by looking at all of these different phonons, looking at the different scattering rates and velocities and so on. All right, and so doing those, we can get very good predictions of bulk thermal conductivity. Here we're matching experiment by fully modeling 3 phonon processes, full scattering terms, not making relaxation time approximations, and so on. And this is relatively recent work here. Right. Now I want to turn to one of the problems that's been fun for us to work on, and this is the whole idea of electro-thermal simulation of transistors, of MOSFETs. Right? And this is one place where approximations to phonon transport really will not work, and let me try and explain why that is. So here is a place where you have to talk about all the granularities of different kinds of phonons, their interaction rates with each other, their rates of transport, and so on. And the reason you need to do that is that Joule heating in your laptop, in your computer, and elsewhere happens because of electron-phonon scattering. Okay, so you apply a voltage, you energize your electrons, they scatter on phonons. But the phonons that they interact with are very, very particular groups. They interact with high-frequency, specific kinds of phonons, longitudinal optical, longitudinal acoustic phonons. And these are phonons that happen to be very slow-moving phonons. Right? And so how hot your computer gets really depends on which phonon groups receive energy because of electron-phonon scattering, how fast they move, and how fast they scatter to other phonon groups. So if you're transferring energy to phonon groups that are slow and that don't scatter very much, then you have no mechanism by which energy can be transported to the boundaries, and your chip then would get very hot. If, on the other hand, you're transporting energy, you're giving energy to groups which either move fast or scatter to faster moving groups, then you have a much lower prediction of temperature. So to get temperature predictions in MOSFETs requires you to sort out who's getting energy, how fast they're scattering, how fast they're moving. Right? And so that's what you need in order, and so you need that kind of resolution of phonon transport. So here I'm going to show you some simulations of a bulk MOSFET in this case, where we have electron-phonon scattering sources from a full band Monte Carlo simulation of electrons. And what we're going to do then is, so this is a description of the phonon generation because of electron-phonon scattering. And so this is a picture of total phonon emission and total phonon absorption. And the difference between these two essentially is the source or the heat source that you have in your phonon transport calculation. Right? So notice then that the phonon heat generation rate is not uniform. There are particular groups that get a lot of the phonon energy. There are other groups that really don't, and how these move, how they interact with each other, how they scatter to other groups determines what the temperature is going to be. So if you were to go off and predict temperature in such a thing, what we find from these detailed phonon calculations is that we predict roughly a 45-degree temperature rise with respect to the boundaries of our MOSFET, whereas if you did this with a typical Fourier model, you really wouldn't predict anything that close. Right? And the reason for this simply is that a detailed phonon transport model essentially identifies bottlenecks in these movement and scattering mechanisms, and that's the reason that, in fact, heat doesn't move as fast as you think it does, whereas a typical Fourier model doesn't, in fact, have these bottlenecks and pathways correctly resolved, and therefore predicts a temperature that is actually far lower than we get. Now, we don't have direct measurements on these scales, but we do have approximate measurements at the gate level, and they seem to bear out broadly the picture that we're painting. Now, what are we going to use these for? What we'd like to do is to use this in informing circuit design, if at all possible. Right? Now, one of the areas in which circuit design, with temperature measurements like this or temperature predictions like this are useful is in this whole business of thermal runaway in microelectronics. So essentially what's happening is that in the newer generation of electronics, one of the big contributors to Joule heating is basically something called, essentially there is a exponential dependence of leakage power, which is one of the big contributors, and the leakage power depends on temperature with an exponential dependence. So what happens is that as the temperature rises, the leakage power rises, increases the temperature, and so on. Eventually, you can actually get complete burnout like this. Right? So however, this temperature that they're talking about is really the channel temperature of the device, and so predicting that correctly is important. However, the channel temperature depends on the thermal environment of the transistor, which of course is coupled to yet larger length scales, and so multi-scale simulation then is a part of this picture. Right? So what we're going to do, so what we have done really, is to set up detailed models of transistors, thermal models of transistors, and then use them to build gates like this. All right, so PMOS or NMOS FinFETs building a NOR gate here, and then from these to develop compact models, which will then be used to make circuits. So you might take NAND gates or NOR gates or inverters and so on, and so hook them up together in a circuit, and then from the circuit essentially go off and predict temperature given the dynamic power of these transistors and circuits, transistors and gates, to go off and predict temperature in thousands of transistors. So going from compact models of individual transistors and gates to build actually the thermal profiles of circuits. And so this is a particular circuit called the XT benchmark circuit, where we're showing temperature distributions as a function of dynamic power. All right, so using these kinds of things, we've been able to predict thermal runaway in benchmark circuits. This is an ALU4 circuit, where we are looking at the maximum temperature as a function of subthreshold leakage. And so depending on the amount of leakage you have in the particular transistor and the activity level, that is the percentage of time the transistor has actually been turned on, we can actually tell at what point we will get thermal runaway in these devices. The same kind of methodology can be used recursively across scales, so you can go all the way from the gate scale of a few hundred nanometers all the way to micron scales and even millimeter scales, going all the way from the SRAM all the way to the cache. Right? So essentially what we're trying to do is to build a multi-scale picture going from transistor to gate to circuit all the way up. A quick word on gas-solid coupling. So one of the other areas that we're working on is the integration of Boltzmann descriptions of phonon transport in the solid with rarefied gas transport in the gas phase. Now this kind of thing occurs in a variety of different applications, nanoporous silicon, thermal transpiration pumps that people are now playing with, nanoparticle beds and so on. You see them in AFM, thermal scanning AFM, for example, where transport at the AFM tip is mediated by the gas around these things. And it's important to understand why phonons and gas molecules may actually compete in these cases. Typical silicon mean free paths are of the order of a couple of hundred, 200 to 300 nanometers at room temperature. The mean free path of gas molecules is on the order of about 100 nanometers, so they both occupy the same space, if you like. In many contact situations, contact resistance between solids is so large that in fact thermal transport may occur through the gas phase, or at least significant amount of it could occur actually through the gas phase and not necessarily through the solid phase. And so the competition between heat transfer through solid phases and through the gas phase can in fact occur in some of these applications. So we've been looking at solving the Boltzmann transport equation both in the gas and in the solid phases together, predicting temperature profiles. So in fact this is actually flipped. The solid is on this side, the gas is on that side, and so no, that's not true. Yeah, so this is solid and this is solid. This is solid and this is gas, and so this is a temperature prediction through the domain for different conductivity ratios, showing temperature jump at the interfaces, and also a prediction of thermal resistance across interfaces of this sort between phononic solids and rarefied gases. I want to talk a little bit about numerical techniques before I quit here. I alluded to this very briefly when I was talking about the Phonon-Boltzmann equation. We are solving, as I said, several thousand Boltzmann equations essentially, one for each of the phonon groups that we talked about. And we also talked about the fact that these phonon groups are coupled to each other through a Bose-Einstein term, and the coupling, the strength of the coupling is by a relaxation time or a mean free path. Right? And the mean free path of these phonons, this is a plot of mean free path in silicon as a function of frequency. These are all the different phonon groups, the red and the blue and the green and so on, have different phonon polarizations. And you see this enormous spread in the mean free path of phonons in the solid. What does that mean? That means that the spread of Knudsen numbers in the solid is extremely large. And so when you solve for these problems, you have to have numerical techniques that can deal with these large changes in Knudsen number. So typical solution techniques are sequential techniques. So what typically people do, only because you can't afford to store 4,000 or 5,000 variables here, is to do things sequentially. So what you would typically do is you're solving, this is the energy form of the Phonon-Boltzmann transport equation for a band with frequency omega and polarization p. And what you do is, and they're all coupled together through a lattice temperature which sits in the Bose-Einstein distribution. So you would start off by initializing the lattice temperature. You'd solve the first Boltzmann band, you'd solve the second one, the third one, and then you'd recompute the lattice temperature, which essentially comes from that term, and then you go back and go round and round in circles when you do that. Right? Now the reason you're forced to do this sequentially is simply that the memory hit on these things is so large. If the scattering time is very small, right, that is if you're talking about a large Knudsen number, then these phonon bands get coupled very strongly because they're all coupled to each other through this Bose-Einstein term. And so typical sequential solution procedures will simply never work. So if you're hoping to compute thermal transport in silicon, for example, beyond about 100 nanometers or so, you simply can't get answers with these kinds of computational procedures. So we've been working on coupled procedures of a variety of different kinds, multi-grid procedures and so on. I want to talk about one particular one that we worked on. This is a hybrid Fourier-Boltzmann solver. And so here, what we're looking at is really a cutoff Knudsen number, below which we will solve for phonon transport through a modified Fourier equation, otherwise through a Boltzmann equation. And the modified Fourier equation is very simple, doesn't have directions and so on, so this is easy to deal with. We solve for that and the lattice temperature coupled, and separately with the Boltzmann equation. And so these coupled solution procedures are giving us enormous acceleration of the order of anywhere between 2 and 100 for these kinds of things. So we're looking at finite volume acceleration procedures for the Boltzmann transport equation. We get really good accuracy with these things. So comparing a hybrid solver with an all BTE solution, we get virtually indistinguishable results with respect to an all Boltzmann solution, and so on. So the last thing I want to say before I close here is that we are also working quite a bit in the area of uncertainty quantification, where we're looking at how to predict output uncertainties as a function of input uncertainties for microsystems. I'll quickly rush through these. This is a prediction of damping of fluid structure interaction in a micro cantilever, where there are large uncertainties in geometry. So here you have a cantilever that's hanging over a ground plane, and the damping that this cantilever suffers as a result of the fluid around it is strongly tied to the gap height, but there are large uncertainties in gap height. These are measurements that came out of our labs. And so one of the things that PRISM is doing is to predict damping versus Knudsen numbery. That's what that is on top, or system pressure. They're the same thing, where we predict not just the mean line, the mean or the nominal behavior, but also to look at the influence of various parameters in terms of their mean and their standard deviations, and therefore to predict not only the mean behavior, but the PDF of damping coefficient. And that's one of the things that's coming out of the PRISM Center. So let me close this out by saying the following. We're trying to build here methodologies and software that addresses thermal transport at the mesoscale and above, so going from several hundred nanometers all the way to microns and greater through a unified Boltzmann equation. We've been looking at compact modeling to allow us to go across scales and to look for acceleration schemes that would actually allow us to go all the way from the mesoscale to the continuum scales. We hope to encapsulate all of this in open source software. The software system is called Mimosa, and we hope to make this available for general use to the research community soon. Thank you.